Thanks again to the organizers, Adil and Simon, for the opportunity to come here and visit. I have known many of you here in person, but many of you I've just only known by reputation and through your work. So this is really an awesome opportunity to meet folks and share work. So today I'm going to tell you or give you an overview of things that we've been thinking about in what we call self-limitation of geometrically frustrated assembly. This won't be enough time to say everything that there is to say about it. So think of this as an advertisement if you want to talk more about things that we know or we don't know. I hope this gives you some ideas of things to ask questions about. This is work done in collaboration with a large number of people. I want to point out Doug Hall, former PhD student, Michael Wang, a postdoc, Nick Hackney, a graduate student, and Chris Tamey, a former postdoc, as well as two collaborators at Brandeis University, Botan Giacotti and Mike Hagan. Okay, so so what we're going to talk about today is related to geometric frustration, which is kind of a concept which has been brought up many times here. And the canonical view of geometric frustration, well, it means many things to many people, but what the perspective I want to give on it is that it's some sort of local order interaction that's preferred locally, but is obstructed, I would say, by topologically, or at least by some loops of interactions, right? Some mutually inconsistent sort of constraints on the system, and they become worse and worse as you get to larger and larger length scales. And so this doesn't necessarily require a lattice. The sort of initial kind of models of this, think about antiferromagnetic Ising model on the train data ladder. We've heard about tetrahedral packing and three-dimensional space, and this is something that Philip and Michael were telling us about. This is kind of a classically known problem, and in here it's thought that there's a problem with packing, and the problem is that our space, the three-dimensional Euclidean space, is not positively curved. If we lived in positively curved Euclidean three-dimensional space, this would not be a problem. And the usual story, and kind of a lower dimensional analog, is we think of a two-dimensional lattice forming on a surface with non-zero Gaussian curvature, right? So a two-dimensional lattice, triangular lattice, would have no problems to form on the plane. But once you form, say, on the surface of a sphere or a hyperboloid or something like that, you introduce frustration. You make equilateral triangular order impossible. And the usual story is that you have to cover this bulk system. And the way that frustration is resolved, as related to what Jonathan was telling us, is through the introduction of singular disruption to the order in the form of topological defects in the case of crystals. Okay, what I want to talk about is a sort of a different class of solutions, which is related to frustrated building blocks, generally speaking, which we call self-limitation. Okay, because building blocks, as they assemble cohesively, they don't have to fill space. They can decide not to, right? And so I'm going to show a cartoon example, and I'll try to show one or two specific examples that we're studying. So this is a cartoon model. So you can think of these as misfitting interacting subunits, kind of like these protein subunits, like a puzzle which is poorly made. Imagine these edges that fit together, they're like cohesive interactions. Every time an edge fits together, this is like a lock-in key binding for a protein. So they get some energy in the system. And you can imagine then that the system can assemble sort of one-dimensionally, but it would form some sort of curvature along this direction. But as it tries to grow into like two-dimensional crystals, very easy to imagine, right? You just build this little tetramer. This one here has a problem, okay? And if these are rigid particles, well, this is it. This is the end of the story, maybe. But in real systems, many soft matter systems like proteins, okay? These are made out of soft building blocks. Their interactions are soft, okay? So there's, in many cases, with some elastic energy that you can pay to deform these things to fit together. And so now you, in principle, can ask, is it better to deform this subunit, pay the elastic energy, and continue to assemble? And so what I'm going to tell you, again, this is a schematic model. I'll give you examples of it. Okay, this is sort of all of the phenomena you need to understand. Okay, there are a class of frustrated models that follow this kind of pattern. We can ask, if I have a bunch of these frustrated subunits and I want to organize these frustrated subunits into self-assembled structures that optimize the energy of the system, or the free energy properly, depending on what ensemble you want to work in, what we can do is group them into subunits of many different domains. Here, I'm going to forget about defects for the moment, okay? And I'm not going to be specific about what is the nature of this structure. In general, there's three types of contributions. For the energy per subunit, there's the bulk cohesive gain of assembly, right? These ones in the middle have lots of sticky interaction, right? This is typically what you get in a crystal. There's some energy penalty per unit volume or area in this case that you pay to the surface energy. You have fewer interactions on the boundary. Okay, and this cost goes as the perimeter, in this case, divided by the area, right? Or in any dimension, this cost goes as some sort of surface energy divided by some finite length scale of the system. Okay, and so this sort of basic idea of minimizing the surface energy costs would tend to favor structures that grow arbitrarily large, right? If you had no additional thermodynamics. Okay, what I'm going to tell you is that in many of these soft frustrated systems, there's an additional elastic energy density penalty, which can grow with size. Okay, and so what does that mean? Well, it means, again, these subunits, they can organize into a cluster, but they have to distort a little bit, right? And the amount by which they have to distort, the total energy cost of that, grows faster than the number of particles that are added to the system. That's a super extensive growth of that energy. And this can happen when you have something pictorially like this. I'll show specific examples of this, where you have gradients of sort of strain or shape misfit in the system. So you can imagine, again, this sort of soft puzzle model. This particle at the outside has fewer nearest neighbors that are pulling it away from its preferred shape, so it's more relaxed, right? But this one in the middle, it's pretty stressed out, right? It's really squished back towards a more compatible shape, okay? And so it's really the kind of the gradients of this structure, the elasticity, that gives it a sort of a secret, sort of long range mechanism to sort of feel how big it is. So that's the story, and it's sort of obvious to now imagine minimizing this function and saying, where's the free energy minimum? And it can be at a finite size. That finite size, there's no length scale in here yet. Okay, that can be bigger than 1 and less than infinity. Okay, and so this is a very potentially useful, but I would argue pretty interesting possibility. Okay, this is not in this talk. It is just a cartoon, but we're also studying models like this, and I'm happy to talk about this. We know a little bit about it, but we actually don't know. We know a little bit about a bunch of things. Yeah. Okay. And so yeah, this basic idea has been around. It's been around for decades, and it kind of pops up from time to time in different contexts. Probably the earliest sort of implementations of it were in the context of models of protein fibers and why they seem to stop growing at a finite clip, right? And so what it turned out in that particular case, it had something to do with what Jonathan was telling us was a preference for a spontaneous double twist of this structure that was incompatible with other types of elastic costs. So something like the blue phase. But the basic mechanism I shows is somewhat agnostic to the details of the geometry. And so I'm not going to go through all the examples. I'm very happy to share more of this with you later. Where things are now and kind of what our point of view on this is that, okay, this mechanism can exist in many different systems. If we had really good friends who were experimental collaborators who knew how to make building blocks of different shapes. Maybe you could synthesize proteins with different shapes and symmetries. You know, usually the sort of basic idea is let's make something that's going to fit together perfectly well, but maybe you can ask your friends, can you make a building block which is supposed to not fit together, right? It fits together almost perfectly well. If I knew and somehow the sort of answer to this question, you give me any type of particle with any type of interactions, any type of flexibility, right? And I can control the amount of misfit in this assembly. If I even know how to measure what frustration means, this is a whole other question. Can I sort of understand how that relates to the sort of the thermodynamic ground states of this system, right? What are the morphologies, what are the sizes, what's accessible, and what are the control parameters? Eventually, or at least in parallel, we're also thinking about how we can sort of translate things that we know, or at least things that we think we know, to communicate to people who use very fancy techniques of making controllable, shape-controlled building blocks using something called DNA origami. I won't talk about this particular example, but I'll show another example. So that's the big dream, okay? And why would we want to do this? Well, the hope is that you could somehow use the intentional misfit of these building blocks to sort of program the self-assembly to stop at a size scale that's much bigger than themselves, right? Maybe for some functional application with controllable photonic properties or encapsulation or fibers or something like this. And there's all sorts of things that would be useful to do with that. I'm not going to tell you about. But there's a big problem with this, and it should be obvious to most of you. So I told you a very simplified story, and I'll tell you a slightly less simplified story, and then I'll give you some specific examples of where this plays out. So I told you that this elastic energy density cost, it grows with size, and I sort of sketched for you that it can just keep growing and growing and growing. And the basic idea of where this comes from is something like, well, in addition to this cohesive energy, there's an elastic cost that grows with some sort of modulus for deforming the assembly away from some preferred arrangement times some average strain squared, okay? And for many models, we know this to be true. And again, I'll show you one. The average strain can be controlled by some measure of frustration. So for these worked puzzle pieces, you can imagine as you make the edges more and closer to 90 degrees, the frustration can go continuously to 0. So there's a nice control parameter. Times some power law of that finite size. Okay, and there are examples of this. But you know, this can't keep going forever, right? Because again, in order for these building blocks to have elasticity in the first place, they have to be soft, right? And so what that means is there has to be some finite amount of energy that I would need to pay to deform them back to some perfectly compatible shape, right? So for the puzzle piece model, the example would be, you know, it can't cost me an infinite amount of energy to deform these into rectangulars or some other quadrilateral that fits together. That's only going to be some finite energy. Okay, so that tells you that really what this energy density, the best it could do is really look something like this, right? It can grow at finite small sizes as some sort of power law, but eventually it tapers off, right? To some size scale where the energy density is basically constant with size. At that point, you know, the self-limitation is going to be inhibited. Okay, so there's some length scale here. And so you can sort of view this by looking at the energy density now as a function of width. Now let's imagine that we have this excess elastic energy in red. Here again is the surface energy in orange. Add them together. If the surface energy is low enough, you have a nice minimum, but now make your particles stickier and stickier and stickier, right? Increasing the surface energy, you get something like this. So those minima, they move to larger and larger sizes, but eventually they reach equilibrium with the bulk state, right? And there are different ways this transition can happen. Some of this happens to be a first order like transition, but the key point here is that there's some maximum amount of surface energy and there's some maximum size, right? So there's really always some sort of upper limit to how big you could potentially use this mechanism to work, right? In principle, it could be arbitrarily larger than the building blocks, but in practice, we don't know what is the sort of true limit in any particular system. And so that is sort of a kind of a key question that we struggle with. And what I'm going to tell you about are sort of, well, maybe one, at least one, maybe two models where we're trying to understand how this can work. So there are at least two classes of escaping frustration. One of them is through these kind of smooth elastic deformations, what we've called shape flattening here, where the particles, as they grow, eventually they realize this cumulative elastic cost is so much that they just say, you know, forget about it. I'm just going to deform to a compatible shape. I'm going to defrustrate myself. But they can also form these complicated sort of singular arrays of topological defects. In general, we don't know which one is the thermodynamically relevant one, right? Which is the lowest energy state that the system is going to find, right? This is sort of a big problem if we're going to potentially use this very useful. Okay, so the first example here is actually I very nicely introduced the sort of a motivation here. So I'm not going to talk about a viral assembly, but we're inspired by this type of self-assembly design. This is work from my collaborator, Seth Braden and Mike Hagan in collaboration with Hendrik Dietz's lab. And they were using something called DNA origami to make these funny triangular particles. They are inspired indeed by Casper and Fluke-like structures, which we've heard about in the last talk. And I think we'll hear a little bit more about updates to that in the next talk. But the basic idea is as shown as follows. So I'm going to show you a little animation of cryo-EM imaging. This is a particle which is made of DNA folded up into a three-dimensional shape. I'd be very happy to tell you the very little I know about that. What's important is that they're able to design very precisely the shape of these particles so that the edges bind specifically together in specific orientations, right? So in particular, they can control the lengths of these edges and their dihedrals. Okay, and so through that geometric design and the lock-in key interactions of those faces, they're able to sort of design capsids of different sizes. And so if you want to really see, does it work? It actually works. Okay, so we wouldn't really be spending that much time thinking about this if they couldn't do at least this. They can make structures that are too big to fit on this slide. I should point out this is not frustrated assembly. Okay, so they're from my point of view, they're cheating. Okay, so these are not equilateral triangles. They make some adjustments to use both mixtures of multiple species of particles with different edge lengths. Okay, but they could just as well decide to work with equilateral triangles. Okay, in which case the system would have to pay some sort of elastic energy to form even these structures. So we thought, well, what would it take to try to engineer such a system to realize geometrically frustrated self-limiting assembly? And so the first idea here is to recognize that, well, if this kind of self-closing spherical assembly, it has one problem, which is that it has no open boundaries, right? So we have to open it up, okay? But we wanted to keep the Gaussian curvature and build this self-assembly out of equilateral triangles so that the Gaussian curvature could generate stresses in the assembly that could perhaps talk to the self-assembly. So we decided to target these trumpet-like structures. So this is a structure that's kind of similar to what we heard in the last talk. It sort of closes itself up into a tube in one direction, but it kind of flares out in this opposite direction. And the question is whether or not we can control the length in that direction. Okay, because that's where the open boundary is. This takes a little bit of engineering of these DNA origami building blocks, but if you basically the point is imagine now you have equilateral triangular subunits. You have to adjust the dihedral angles. So some of these have to be sort of convex and some of them have to be concave, and you can map that onto some preferred local shape tensor or some approximation of a surface. Okay, so we know how to do that in principle. We made some progress in practice. In practice, we're sort of halfway between here and here. We made tubules, so we know how to make the zero Gaussian curvature versions of this. This is an interesting story in and of itself, but again, here there's no accumulation of energy along the length because the system is perfectly periodic. All of these are kind of screw symmetric. You know, once it fits together, it can keep running. Okay, so now the question is, if you introduce some additional preference for curvature along this axis, can you use that to generate tubules that know how long they should be? Okay. So the way we start is we start with I'm a theorist, so we start with a very simple continuum elasticity theory that has a sort of minimal ingredients of this. We assume very high symmetry because we can only solve like ODEs, or at least we're only willing to solve ODEs. It's not quite true. Okay, but and so the basic ingredients are very simple. There is we think of this as a tubule. It has some sort of reference hoop curvature, but remember there's a preference for negative Gaussian curvature. So it means that the deflection away from this should have a preference for a kind of a curvature along this axis. But in order to do that, remember this is sort of made out of triangles that are equilateral, so it's going to have to build up strain along the hoop direction, right? So in the absence of any defects like dislocations, right, the distance between the triangles on the outside would be different than here, okay? And you can show fairly simply that it's of this form. For any experts in the audience, this is precisely sort of the what's known as the kind of Pople-von Karman elasticity, which is a version or an outgrowth of Gauss's theorem of Grigio, which says that if you have an elastic membrane and you try to force it to have Gaussian curvature, you must not only generate stress, you must generate gradients of stress. Okay, and so this, of course, is the key, is the gradients of the stress, which are necessary in order for the structure to know how big it is. Okay, so if you solve this equation, You go to the Lagrange equations as you like. You get something like this for the elastic energy density as a function of size. For very small sizes, essentially this term wins. This hoop stretching energy is not so bad. It's willing to pay that stretching energy, so it absorbs the Gaussian curvature. But eventually the growth of that stretching energy, which grows chordically with the length, is too much, and it decides to flatten out, and it sort of pushes the frustration to the boundary. Okay, and you see this transition at a length scale, which is related to the ratio of these two elastic constants, the bending versus the stretching in the material. And so what we can of course do is go back to our thermodynamic model and say, well, what is the maximum size that I could get as I make these edges more and more sticky? And this maximum size is proportional to this elastic flattening length. Okay. And of course, we can relate this to these material parameters. We can relate it to the geometry. So that's what theorists do. We kind of raise on simple models, but this is how might this really work? So this we had to ask for some help, right? Because these real particles undergoing self-assembly, they're not required to obey the assumptions of any theory. They're built out of discrete building blocks. They fluctuate at finite temperature. They come on and off. And so this is a very simple model of these triangular particles, which are designed to mimic this type of assembly. It was developed in collaboration with Mike Hagan and a postdoc in his group. And so there's two different edge types here. These green edges, they form bonds along the length of what we call these trumpets. We've thought for a while what the name of these subunits should be. From time to time, we think it would be funny to call them trumpemers, but maybe this is not the way. I don't know. Yeah, no more further comment. And so these things can bind together. They have different binding energies between the reds and the greens. And the preferred dihedral angles between the greens and the reds are such that they have a preferred local curvature that's the negative trumpet lighting. Okay, so the model is very simple. It's a dynamic Monte Carlo, which we consider one cluster of the assembly in which can exchange monomers within a bath at a fixed chemical potential of free subunits. So what you'll see in the simulations is a single cluster, and randomly subunits will add or be removed from the boundary. These subunits can stretch, they can bend at finite temperature. Okay, so we're trying to figure out whether this could potentially be realizable in these systems. And so what I'm going to show you is that, of course, it depends on sort of where you are in the parameter space. So I'll show you movies of two things on the left, a limit of low frustration on the right, a limit of high frustration. So first, focus on the left. What you're seeing in these subunits, the ones that are colored purple, they're colored purple by the local strain. The ones that are yellow are strained, right? So what you see as the structure grows larger and larger, it unbends. It's flared a little bit at the boundary. That's because the target curvature is relatively weak. Okay, so the amount of frustration is so weak that the bonds are so sticky that it just says just flatten out and grow farther. Okay, so this structure will just keep growing forever. It's effectively just a tubule. The structure on the right, if we go back, well, you'll see it has a very high frustration, so it does form a self-closing trumpet, but the frustration is so high that it cracks the bonds along the hoop direction. And you can sort of watch visually here at the end. What it does is it cracks the bond, but it nucleates another baby trumpet off that structure. So that will form a second trumpet, and then of that, of course, will continue to form this chain of trumpets. That is an interesting structure. It's not limited in mass. It's limited in some sort of structural features, but we might ask, can we use this for length limitation? And I wouldn't be standing here if we didn't think we could. So if you basically tune things sort of in this intermediate range where the frustration is not too big, not too small, you also have to add slightly stickier bonds along this hoop direction. You can get conditions where the structure will at some point reach kind of a equilibrium, a steady state of binding and unbinding to find this structure where it stops.
Greg, sorry, in that picture, where is your the gradient of elastic energy that you were talking about?
Ah, very good. See if we can get to it. Yeah, so what you'll see here at the end is that these subunits here in the middle, they have a slightly different color than the subunits on the boundary. This is actually, you're getting to a good question, which is that I told you at the beginning that there's a gradient in this structure, and it's very hard to perceive a gradient on a structure that's sort of a word. 1 or 1 to 3 to 4 to 5 subunits Y, right? And this is really kind of where a major challenge of the problem is that these are always built out of discrete subunits, right? And so these discrete subunits are 2 or 3 or 4. This kind of gap between, let's say, the kind of continuum mechanics formalism and the discrete geometry, well, it becomes difficult to interpret sometimes. Okay. Nevertheless, I guess so you can look at these trajectories. This is the structure as a function of time, the number of subunits. This one, you can see it just reaches a certain size, it stops growing. What's important, and you have to do a lot more work, is you calculate the free energy as a function of size. So for this blue curve, and you can see that indeed it has this finite minimum as a function of size. So it does have the ability to sort of sense its size. Things are more complicated than what this continuum model will tell you, but of course they're more complicated than what they can do. The question is whether it tells you anything that's useful that you could engineer. Okay. So what I'm just here summarizing is that what we could do in principle is use these models to try to map out parameter space that would be useful for telling the experimentalist. We have to tell them that frustration should be neither too big. So this is big frustration down here. If it's too big, the structures are too small. If it's too small, they'll just run away by flattening out. And if the binding energy is not sort of sufficiently anisotropic, right? So in this case, you need stronger hoop binding to suppress the formation of cracks in the system, then the system runs away through another instability. Okay, so these are lessons that in principle we can translate to experimental colleagues. So I'm probably doing terrible in time. I would like to take another minute or so, two? Okay, wow. To show you 1 second perspective on what this looks like, okay, and just show you another class of model that we're thinking about. I'm going to skip over this, but one question you could ask is, well, these structures, they're sort of of order of a few subunits in width, right? Like, could we get them to be an order of magnitude larger? This is something that we're working on. I won't tell you about it, but it has something to do with kind of engineering the elasticity of this assembly by introducing floppy modes into the structure. We know a little bit about this one again, but this is work in progress, and it works in principle, right? At least in computers. Okay, so the last thing I want to tell you is that we've been thinking for a long time about whether we can really understand the system from a statistical mechanical point of view. Right? Everything I basically told you, you can think of it as a zero temperature argument, but self-assembly takes place at finite temperature. Entropy is necessarily important. And also, as I mentioned before, we have to think about these other mechanisms of escaping frustration through the formation of kind of more complex arrays of defects, which happen in discrete systems. So we've been searching for a very simple model. This is what I think is the simplest model of frustrated self-assembly. It's a lattice model. You have subunits on this model at a fixed concentration. They need a simple shape degree of freedom. And our simple shape degree of freedom is essentially an XY spin, which you can show with a color wheel or with an arrow. Okay, the subunits, they float around the lattice. They have a lattice Hamiltonian. Don't need to worry about this equation, but basically they can have some sort of nearest neighbor interaction that is independent of their orientation. But like in a ferromagnet, they also have a nearest neighbor interaction that depends on their relative spin orientation or phase. Okay, except that there's a preferred offset, if you like, a preferred phase winding that depends on which of these bonds that are in the system. Okay, so this is kind of a lattice gauge model. And so what does this look like? So if you design your system so that these gauge interactions have the property that if you sum those preferred phase mismatches around a loop, and there's a non-zero sum, that's a non-integer multiple of 2 pi, you can introduce frustration. So it looks kind of like this, right? So here, imagine I'm trying to follow the preferred phase winding, and I come back to myself, and what you'll see is that there's a problem. Right, this thing doesn't close on itself, and the problem gets worse and worse as it grows. Some people will recognize this is very much the same as the problem of parallel transport of a vector on a hyperbolic surface, and there's a mathematical mapping between them. If you take this model and just sort of simply anneal it, so this is what the strain energy looks like. There's a lot of elastic energy here. When you anneal it, this is just Metropolis Monte Carlo. It organizes into this type of strain gradient pattern that I told you about. Okay, so Last thing I'm going to show you is just what happens when we actually turn this 10 simulations on at fixed concentration. It's very easy to see what it looks like. So first, no frustration. What happens is, well, the usual thing, right? At low concentrations, the system is in a gas. At high enough concentration, it condenses into a coexistence between a condensed droplet and a vapor, right? And then if you watch over time, this will just ripen into a single droplet. Now what happens is we stay at the same 4% fraction, but we're going to crank up frustration, right? But same concentration, temperature, model parameters. So what happens is the system disperses again, right? You've just essentially raised the energy for the system to aggregate, so frustration could redisperse the system. Maybe that makes sense. But if you then go back to higher concentration, you see something like this. Okay, you run the simulation, but you see with these aggregates, these are not bulk droplets, they form and unform. They are self-limiting in their width direction, but they're not self-limiting in their length. Okay, so you see these fluctuating populations of branchy worms, polymers, if you like, but they know how wide they should be. Okay, I won't say more about this except to say that we understand what this should be. It's like things that other people have seen in geometrically frustrated assembly. Some people might know Vinny Manoharan's work on this system. This happens in many frustrated systems. It happens here for the same reason. The last thing I'll leave you with is if we now stay at this system for high frustration where we have self-limitation, but then we drop the frustration, we try to go back down, what we see is this thing. Okay, so it condenses, but it condenses into a defective phase. So this is a sponge morphology. Okay, and if you zoom in on these structures, and I won't have time to show you, and you look at the phase, you can see that these are actually vortices. So these are topological defects in the system. So this is this secondary mechanism by which these systems can screen frustration. I'll leave you here with this kind of overall sort of mosaic phase diagram of what little we understand about kind of what the concentration, temperature, frustration landscape looks like. We have these array of kind of defective bulk states down here, dispersed subunits up here, and the self-limiting phase down here. There's all sorts of unexplored territory up here, and we know nothing about kind of critical phenomena. But this model is almost simple enough that we can study it as a statistical mechanical system, and we think it has almost all the elements that you need to start to understand frustration in much more complicated systems. So sorry for running over. I'm going to stop here and acknowledge all the folks who did this work, and in particular funding from the National Science Foundation, and thanks for your attention.
So there's two questions on this, please. Yeah, right.
So, Greg, a really fantastic talk. Why is this used for frustration actually to regulate assembly? So a simple system is the MS2 viruses, which come from dimers. There are two types of dimers, and the only difference is that where they meet at the fiber axis, an FG loop has to flip. And what happens here is that these packaging signals, I'm not talking about today, but you heard me talk about on Monday or other occasions, actually help the switching between those two conformers and just regulate frustration in the sense that they relieve frustration where necessary to form the 5 poles. But what's really interesting is that frustration then is important for release as well. They have to, in a coordinated way, release those contacts in order to break the curve set up and losing that frustration angle. So what you're hitting on with this talk is super important in this system.
Yeah.
Looking forward to hearing more about that.
Yeah, I mean, the general idea is that basically nothing anybody's made is not frustrated. It's almost impossible to make something not without a little bit of the question then is kind of where does it go? Does it just kind of change the sort of renormalize the sort of cost of assembly in some not in trivial way, right? Shift sort of, let's say, chemical potentials that are between different states, or can it give rise to different emergent behaviors? And this is kind of the questions that we
Not kind of controlled by the RNA protein interactions,
Yeah.
right? So the virus really controls that phenomenon
Yeah.
to its advantage.
Great. I'd like to hear more about that.
Would you like to comment?
Yeah, maybe.